Hi, everyone. My name is Gellert, and I work with Jeff on this project. We called it Predict Blood Donations, and we entered a competition from Driven Data. And so what I wanted to do is, or what we wanted to do is show you what we've done and the results we got. So in terms of introduction, we wanted to talk to you about the fact that there's a significant gap between the blood supply and demand. You can see here that about 4.5 million patients get blood transfusions each year in North America, but the number of donors who donate blood each year is actually limited. A lot of blood is being used, and there's a significant gap. Now, we also found that the shortage is not a unique problem, and in fact, the problem that we're looking at is actually from Taiwan. The purpose of the study was to accurately predict whether a donor who donated in the past will donate again based on a couple of variables, and we only had 4 variables here. One of them was the number of months since the first time a person donated blood. The second one was the number of months since the last donation. We also had some numbers in terms of the number of donations and the total volume of donations that was given. And we'll talk about the fact that the last 2 were actually correlated. In terms of the data set again came from Taiwan, and it was actually a randomly selected a group of individuals. In fact, there were 776 of them. This number came from a very large database, and we received the data from Driven Data. The 776 observations or subjects were partitioned into 576 training observations and 200 test observations. And what's interesting about it is that the target variable, which was whether somebody donated blood or not in 2007, was not really given for the test data set. And that is how the accuracy of our model was basically judged in terms of a comparison of our predictions versus the actual donation behavior of the 200 subjects. So what I wanted to do is show you some exploratory data analysis on some of the variables. So what you see here is the first variable, which is the number of months since last donation. And the very first thing that's very striking here is that the data is not normally distributed. It has a very large number of zeros. So a lot of people are I guess it took a long time, or they haven't really been donating in the most recent couple of months. And the other thing that's striking about here is that the data is multimodal. So you have 3 peaks, and you can see a histogram as well as a box plot of this and a QQ plot of this. So we did some transformations of this data. The data was log transformed. We also standardized it and removed some of the outliers. So we could cure all the issues. So you can see that we still have multiple nodes, but at least the data is sort of more normal. And on the right-hand side at the bottom, you can see that the outliers have disappeared. This particular chart shows, or page shows, the second variable, which is the number of months since the first donation, and it also has lots of problems. This variable was also not normally distributed, and it has some outliers. But once we transformed it, on the bottom, you can see that the distribution actually became almost normal. We also standardized the data, and once we were done with it, the data became almost normally distributed, and basically there are no outliers here. The last couple of variables is the number of donations and the volume that was donated. And here, this data set or this variable is also kind of right-tailed, so it's not normally distributed. It had lots of outliers, and so we attempted to transform it and standardize it, but it became still it remained still skewed. But at least it was a little bit more close to normal than the original data set. So the other thing that I wanted to point out here is that the two variables, the number of donations and the volume that was donated, is 100% correlated, and that's because what we discovered is that every time somebody went to donate blood, they actually donated 250 cubic centimeters of blood. So basically, every donation just multiplied by 250, and that gave you the volume. So it's basically the same variable. In terms of the data prep, so first we aggregated the training and test sets together for data preparation, and we also created some additional variables, and I'll see a couple of them that we created. So we looked at the number of years since last donation, because the original variable was actually the number of months since last donation. We also looked at whether somebody's a first-time donor or a repeat donor. We looked at a ratio of months since last donation to first donation, and also the number of donations per month. Again, we talked about the fact that we removed some of the outliers, and we also transformed the data. But once transformation was completed, we then went into partitioning the data set into three subsets. So we had the original test data set with the 200 observations, but we also took the remainder, and then we cut it into two subsets, if you will. One was basically the training data set on which we trained the model, and we also created a validation data set which was used to judge which model to use and whether we should do some extra treatment to some of these models that we built. I also wanted to point out the way we standardized the data set. So basically, we used the mean and the standard deviation of the training data set, and that training data set mean and standard deviation was used to standardize both the validation and test data. In terms of model building, we use something that's called recursive selection, which is part of the Carrot package, and it was actually particularly useful because we didn't have a lot of variables to use. The Carrot package is using a backward elimination approach, and when we did this, each model's accuracy was computed, and for that we use something that's called a log loss function, and that was actually assigned by the competition.
Okay. I'll talk a little bit about our model selection and our results. So we tried several models when we started off. We tried to keep up with tried some of the models that we were talking about in the textbook, as well as some other classification models that are pretty popular. As Gellert talked about, we evaluated our models on two metrics. Originally, we were using the accuracy metric, and then we ended up changing to the log loss metric because that's the metric that's used by the competition itself. And we were finding that some of the models that were actually the highest accuracy performers didn't perform as well when we used the log loss metric, and we noticed that when we would submit our model for grading, and they weren't scoring as well as we thought they would. The log loss function is a little bit different than the accuracy because it's a very steep penalty in terms of false classifications. So that's part of the reason why maybe some models that were maybe more accurate, if they were falsely classified a couple of records, you get a steep penalty, which would result in a worse score. In terms of the scores, our top three scoring models in the log loss were off to the right in the right-hand corner. And based on the mean and the median, it looked like the GBN would be our highest performing model. But when we actually submitted it, the AVNNET, which is the average neural network model, was actually the top performing model. So that is the model we're going to talk a little bit more about. So I'll explain a little bit about what a neural network is. So a neural network is an interconnected group of nodes. It was originally modeled in the likeness of the human brain. It's an iterative learning process. It takes one record at a time. It cycles through. It assigns weights, and then it keeps going through and adjusting those weights until eventually it converges and it finally says there's no more use adjusting the weights. We've basically kind of leveled on the improvements that adjusting will happen. If some of the advantages of a neural network, it's got a high tolerance for noisy data. And as you see in the little graphic, basically what happens is in a forward propagation, which is the most common propagation method for a neural network, you start off with your input units, which are essentially your variables. Then you've got these hidden units and then output units. Each one of the edges are assigned a weight. Those weights are multiplied by the inputs and then summed up, and then you apply an activation formula to each individual output, and we'll talk more about that. This particular network that you see on the screen actually has 4 hidden layers. So each vertical column is a new hidden layer. This is a very complex neural network, and it's because it's got more than one layer, it's considered a deep neural network. Each layer has a different number of nodes. So for instance, this layer, the first layer has 5 nodes in it, and then each layer you can count has different number of nodes. So our actual neural network is off to the right here. So not nearly as complex as the previous graphic. We use 4 variables for the inputting into our neural network model: the ratio, standard deviation of the month since first donation, standard deviation of the month since the last donation, standardized donations since last donation, and the standardized donations per month. Each of these numbers here are the weights that are assigned to each of those variables. And then this here, the 1 in the upper left-hand corner is the bias, and there's a weight assigned to the bias as well. So the input layer is, as I said before, is usually the number of nodes plus this bias variable. Bias in the classification is always 1. The hidden layer is the outputs that are connected to those inputs and by some weights. Initially, they're chosen at random, and then the computer cycles through them iteratively until it adjusts to find the best fitting model. The number of layers is usually 1, but sometimes, depending on what you're trying to do, you can have more than 1 layer, and as I said before, this is called a deep neural network. In terms of number of nodes, it depends, but typically it's somewhere between the number of inputs and the number of outputs. The drawback, if you have too few, you don't have enough flexibility in the model to account for some of the variation. And if you have too many, you risk overfitting. In terms of actual calculation, so you have this formula from the book. I rewrote it in a little bit more readable function, which is just the summation of the W, which is the weights, the individual weights of all of the inputs, multiplied by the input themselves, plus the bias. You take all those values, you sum them up, and then you apply this activation function sigma. For a classification model, the activation function is the sigmoid, which is 1 over 1 plus e to the negative x. And the reason that function is used in classification models is because of its graph. If you look at the graphic, it's a nice little S-shaped graph with values between 0 and 1, which fits perfectly in a classification method. So here's a sample calculation using this function. So here we have our input values for ratio, month since first donation, last donation, per month, bias, etc. You take all those input values, you multiply it by the weights, as you see in the graphic off to the right. So the fourth column here shows you the input times the weights. Then you take the sum of all of those values, you get some number, negative 7.299. And then from there, you take that value and plug it into the sigmoid function, which gives you the 0.00675. What this value is the value of your hidden node. In this case, we only have 1. If we had multiple hidden nodes, you'd have to repeat this function for every single hidden node. So what this value, the 0.006, is it's this middle node right there. And so now we have to do the same calculation on that node. So that's shown in the bottom. So we've got the hidden node value of 0.000675 multiplied by its weight. You've got to, again, have the bias variable multiplied by its weight, do the same calculation. Take the sum of that, 0.57610, and you again apply the sigmoid function, and you get a final value of 0.64. So what that's saying is, given these inputs in the second column of the first table, given those inputs, we have a 0.64 probability that we're going to have a donation made in March.
So one of the things that we did was we didn't want to just take the winning model here, which was the neural network. We actually took some models and we tried to create them without the help of the computer, and just use the regular machine learning techniques that were described in the book since the start of the quarter until now. And so you can see a list of models that we tried here. The first one was k-nearest neighbors. We also tried LDA and QDA. We fitted some polynomial models, natural spline and some splines and some smoothing splines. Both of those were using the GAN package. And so what was really not too great is that none of these hand-fitted models could beat the neural network in terms of accuracy or in terms of the log loss function. So at the end of the day, we still decided to submit the AVNNET results.
For final conclusions as to how we performed with the AVNNET, out of the 3,823 competitors, currently we are ranked 69, which is just under the top 2 percentile. Our top score in the log loss was 0.4307. Our team name was the NW Data Science Classifiers. So feel free to check us out. And thank you for watching our video.
Thank you.